Okay, Chem 12s, here is your final question from yesterday. You are asked to find the concentration of the hydronium ion in a 0.20 molar solution of potassium nitrate. However, this is a salt, so right away you can see that there is no hydrogen to donate as an acid, and there's also no hydroxide. So the salt in itself is not an acid or a base. However, you put it in water and it will dissociate. So that is the first thing we will do. So if KNO2 is put in water, as soon as one note decides to respond, you will get potassium ions and the nitrate minus ions. So out of these two ions, only one is going to be able to give us hydroxide ions. In order to produce hydroxide ions, the water will have to give up its proton. Well, it's not going to give up its proton to potassium because that would be two positives. So it will give up its potassium to the nitrate. So your reaction then will be the NO2 minus plus the water will react to give the HNO2 plus the OH minus. So again, the only one of those two ions that could possibly give us this and this was the nitrate ion, because the potassium, of course, would give us an acid instead, and that would not help us find the concentration of the hydroxide ion. Okay, so now that we have this, we can do two different sets of calculations that will come together. The first thing we need is our ice table. So we draw our ice table. And of course, water is negligible because it's a liquid. And now we can plug in the values that we know. So we do know that we start out with 0.20 molar solution of KNO2. So if this is 0.20, then we know when it dissociates, we'll have 0.20 molar because of the 1-to-1 ratio. So we start off with 0.20 molar, and of course we have 0 HNO2 and 0 hydroxide ions to start. Now we don't know what the change will be, so our change is going to be X. So the NO2 will go down by X, whereas the HNO2 will go up by X, and so will the hydroxide ion. And so then we know our final concentration of both the HNO2 and the hydroxide ion will each be X, and we know that our NO2 concentration will be 0.20 minus X. So now we are ready to find our expression for Kb. So Kb will be equal to the concentration of the HNO2 multiplied by the concentration of the OH minus divided by the concentration of the NO2 minus. And we can plug in our values from our ice table, and both our products on top will be x. So we will have x squared divided by 0.20 minus x. So this would all be good if we had a value for Kb. Kb expression, which is the Kb is equal to Kw divided by the Ka of the conjugate acid, which we just look up from the table. So Kw is 1.00 times 10 to the negative 14, whereas Ka from the table, and you look it up for the HNO2, and we can see that it is 4.6 times 10 to the negative 4. So if you punch that into your calculator, you get a final value of 2.174 times 10 to the negative 4. So that is what our equation is equal to now, 2.174 times 10 to the negative 4. And we have to solve for x. But again, you see we have the same little problem of having x squared on top and an x on the bottom. Okay, and again, we can say that this is negligible for the same reasons as yesterday. So our final expression is x squared over 0.20 is equal to 2.174 times 10 to the negative 4. And then when you solve for x will be equal to 2.1 times 10 to the negative 6 molarity. And you might want to pause this in order to calculate the pH, because of course this is just your concentration of hydroxide ions. It is not what they asked you in the question, which was to calculate the pH. So from this, you can calculate the pOH, and then you'll remember from yesterday that that will give you the pH, because the pH and the pOH must equal pKw. So pH plus pOH have to equal 14. Okay, for the last one, at a certain temperature, you have a 0.20 molar solution of potassium sulfate. It has a pH of 10.25. Calculate the Kb of the SO3 2-. So we know that if we put the SO3 2- into water, we will end up with HSO3 as the conjugate acid, HSO3-, sorry, plus the hydroxide ions. Okay, again, we need our ice table. And we know that we start off with an initial concentration of 0.20 molar sulfates and 0 for HSO3 and 0 for OH-, and all our waters are constants. So now we just need to find out what our change is, which we could if we knew the values here or here. But in this case, we can do that because we will know our final concentration of our hydroxide minus ion because we were given the pH. Now we can't go directly from pH to POH, from pH to concentration, but we can if we use the POH. So on the side here, if we want to find the pH or POH, then 14 minus 10.25 will give us the POH, which is 3.75. So then the concentration of hydroxide will be equal to the antilog of the POH. So 10 to the negative 3.75 will give us our hydroxide concentration, which is equal to 1.778 times 10 to the negative 2. Actually, I mean 4. So our final hydroxide concentration is 1.778 times 10 to the negative 4. So our final concentration of our conjugate acid is 1.778 times 10 to the negative 4, which is what our X is. So this went 1.778 times 10 to the negative 4 and 1.788 times 10 to the negative 4. So our change for the SO3 minus ion was also 1.778 times 10 to the negative 4. So we can find out our final concentration, which is 1.998. So now we'll just skip a little bit down below to do our Kb calculation. So our Kb is the concentration of HSO3 minus multiplied by the concentration of OH minus divided by the concentration of SO3 2 minus. And now we plug in our values. 1.778 times 10 to the negative 4 squared divided by, 0.1998, and KB is equal to 1.58 times 10 to the negative 7. And of course there's no units for KB, but didn't. It only had 2. So this would be 1.6 times 10 to the negative 7.